Hello, and welcome to another Introduction to Astronomy lecture. This is lecture number 14 on the interstellar medium, that is, the space between the stars. In today's lecture, we will learn about the difference between interstellar material and the interstellar medium. We will talk about the density of the interstellar gases and dust that are between the stars, as well as the different types of regions of interstellar gas, such as H2 regions, neutral hydrogen regions, and ultra-hot regions. There are also dust clouds and dust nebula, which have effects on radiation. And there's also sources of cosmic rays, which help in the cosmic baryon cycle. And lastly, we'll talk about our local bubble in the galaxy, which is that space around our solar system and the nearby star systems. So we think of space as often we think of it as being empty, but it's not. Even though there's vast distances between the stars, the space between those stars is still filled with stuff, even if it's diffuse. And so we call this material between the stars as interstellar matter. And then all the space which collects interstellar matter is referred to as the interstellar medium. So some of this interstellar matter has coalesced throughout the galaxy into large groups and clouds, which we call nebulae. But not all nebulae are static, and they're all constantly evolving. They're reshaping, growing, dispersing, and merging together due to the gravity from their own mass and external forces, such as intense radiation from stars. This motion creates a cycle of the interstellar material throughout the universe that is constantly coalescing and then redistributing itself. And so the space between stars is incredibly vibrant with activity. The density of the interstellar material is quite thin. So most of it, 99%, is gaseous, and it's primarily hydrogen and helium. The smallest fraction is solid material like dust, and it's typically rock silicate or graphite surrounded by reduced iced compounds. If you remember, we talked about reduced iced compounds in the outer solar system planets, specifically with the ice giants Uranus and Neptune. Interstellar gas is only a density of about 1 atom per cubic centimeter, while interstellar dust is far less numerous, with only a few hundred grains per cubic kilometer. However, the interstellar material overall is patchy and irregular. It's not very evenly distributed. That's just those previous numbers were just average numbers, and so that can be a little misleading. The density of an interstellar cloud, like a nebula, can be as much as 1,000 times more than that of normal space, but it's still virtually empty relative to the densities of gas that we have here on Earth, which the densities of gas here on Earth is up to 10 to the 19 atoms per cubic centimeter. So there's a huge difference between the densities of the air here on Earth and the densities of gases out in space. But since this density, even though this density is very low, there's still a lot of stuff because it occupies a huge, huge, huge volume. So it still adds up to quite a bit of stuff. And so just to think, this material is in between stars, and stars are very far away. So there's 4.24 light years between our sun and the nearest star, Proxima Centauri. So this amounts to 4 times 10 to the 13 kilometers away. So even if we have 1 atom per cubic centimeter, that's going to be just even larger amounts of centimeters. I think 10 to the 15 or yeah, 4 times 10 to the 15 centimeters away. So large distances, little bits of stuff, but that still adds up to lots of stuff. We're now going to talk about H2 regions. So if you remember, H2 is for this ionized hydrogen, and so this is going to be visible gases near hot stars, where we see strong Balmer lines glowing in the red. Due to the radiation from the hot star, the surrounding gas is heated to nearly 10,000 Kelvin, and so this ionizes the interstellar gas. Nearby electrons are captured, and this retains the hydrogen spectra for this temperature despite the ionized atoms. These interstellar clouds are named based on the amount of ionized atoms present. So an interstellar interstellar gas regions surrounding hot stars are referred to as H2 regions, where the 2 refers to the ionized hydrogen. 1 is reserved for the neutral state, and then the higher numbers are reserved for higher ionization states. And so we have an image of an H2 region around a star in the lower left. And so as electrons are captured by the ionized hydrogen, they cascade down in energy levels, and this is a process of ultraviolet emission to visible light, which is referred to as fluorescence. And this allows the clouds to be easily observed. However, most nebulas are not close enough stars for the hydrogen to ionize, and so we have a lot of regions with neutral hydrogen. And neutral hydrogen does not typically or emit or absorb light in the visible spectrum. However, it was seen in 1904 that other elements in these nebula can still absorb light and be observed. And so this is where we look for calcium and sodium atoms in the nebula to find their absorption lines. But calcium and sodium are much rarer and difficult to detect in sufficient quantities for them to be detectable in these gas clouds, and so we still needed a way to detect neutral hydrogen. In 1944, Hendrik von der Holst predicted that neutral hydrogen atoms might emit a very long but strong radiation wavelength at 21 centimeters due to changing of parallel and anti-parallel spin states of the proton and the electron in the hydrogen atom. And so in 1951, they found these 21 centimeter hydrogen lines using radio detection methods, and they were able to finally detect H1 regions, or neutral hydrogen regions of interstellar gas. So now we're going to talk about ultra hot regions. It may seem that the H2 regions we talked about were very hot since they were about 10,000 Kelvin. However, there are even hotter regions of the interstellar medium which can reach nearly a million Kelvin. Ultra hot regions were first noticed due to their really surprising amounts of ionized hydrogen or ionized oxygen, which was ionized 5 times, oxygen 5. To strip away oxygen of 5 electrons would require a huge amount of energy, but since their discovery of these since their first discovery, many of these high energy bubbles have been found in our own galaxy. So theorists have shown that these ultra hot regions of interstellar material are produced by the biggest explosions of stars during their death. These are supernovae. Supernova explosions launch gas into interstellar space at tens of thousands of kilometers, which collide and heat the surrounding medium to these temperatures that are in the millions of kelvins. These explosions are estimated to occur roughly every 100 years in our galaxy, and so this creates huge shock waves and turbulent motion in the interstellar medium, which really churns up the interstellar medium and helps spur new star formation while also enriching space with these heavier elements and materials that we need such for life, such as the iron in our blood that came from the deaths of very heavy stars dispersing their iron out into space. Or if you have jewelry, any gold or platinum that is in your jewelry came from violent supernovas as well. We've been talking about gaseous regions. There's also very dusty regions. These are dark regions in space which sometimes appear as voids of stars because when we view them from our perspective, we just see a black cloud. We don't see any stars shining from behind them because this dust is blocking out all of the visible light. The densest, darkest of these clouds are called dark clouds because they contain large amounts of tiny solid dust grains, which become opaque to light in the background because they either scatter or absorb that incident radiation. Dark clouds are too cold to radiate energy in the visible spectrum. However, they do glow very bright in the infrared since dust grains can absorb radiation and re-emit the absorbed radiation in the infrared near 10 to 500 Kelvin. So this is where a telescope like James Webb is very good at peering through these layers of dark clouds because the infrared radiation that James Webb looks at is able to go through these dark clouds, whereas an optical telescope like the Hubble cannot see through these dark clouds. Some dust clouds are near to luminous stars and scatter enough light to become visible in what we call a reflection nebula. So, for instance, the Pleiades, which we see on the right, the brightest stars in that cluster are illuminating the dust cloud behind it and creating a reflection nebula in the blue wavelength, which is the most common wavelength for scattering. But also, the stars in the Pleiades are large, hot, massive stars, and so they are also primarily blue stars. And then if we look on the left, we can see a dark cloud that is very much a dark cloud. So now let's talk about interstellar and extinction and reddening. These are effects that the interstellar medium has on light as it travels from distant stars to us. So as we know, when radiation from stars interacts with these dark clouds, it's either absorbed or scattered by the dust grains. So this leads to an increasing fraction of this light from background stars not reaching us. This is an effect known as interstellar extinction. So when stars are nearby to dust clouds, they often appear redder than their spectral types would suggest, because they should be hotter than the red star light that we're seeing from them. And this is due to the dust around them not only dimming the wavelengths but also reddening them. Because of the scattering of the blue wavelengths, it's really leading to only redder wavelengths making it through these dark clouds. So this reddening suggests that long wavelengths of radiation, which are less affected by these dust clouds and interstellar extinction, can be more efficiently studied than short wavelengths, which has led to an emerging field of infrared astronomy, which is where the James Webb is thriving. So we can see an example of this interstellar extinction and reddening when we look at the image on the left, where we see this red blob right there. So when viewed in the optical, that red blob is actually a dark cloud. However, this is a composite image, so what we're seeing through that red blob is actually the infrared light that is then being added to this image. So around it, we see the visible light, and then that blob would be the dark cloud where we're seeing only the infrared light coming through. So that is some extinction and reddening in one, because it's extincted the optical wavelengths and has led to only the infrared wavelengths making it through and being redder. But the interstellar medium is not made up of just dust and gas. It is also home to another type of particle known as cosmic rays, which travel at extremely high velocities through space. First discovered in 1911, cosmic rays were found arriving to Earth from outer space, and they were not from our sun's radiation. Most of these cosmic rays are atomic nuclei that are actually traveling at nearly 90% of the speed of light. The majority, 90% of these cosmic rays, are simple nuclei, while heavier nuclei make up the another 9%, and the remaining 1% are particles near the mass of the electron. This includes many positrons, which is the antimatter counterpart of the electron. Cosmic ray energy is only 1/1000th the magnitude of our sun's radiation, relatively close to the scale of stellar radiation from other stars, which supports their theory that cosmic rays are indeed coming from other stars and not our sun. The exact origins of cosmic rays are really difficult to determine. While photons radiating from stars follow a linear path, charged particles like protons and electrons can have their direction as they travel through space changed and curved by magnetic fields. This means that the path of cosmic rays are often really curved in interstellar space and are even influenced by the Earth's own magnetic field as they get closer to us. So when we observe them, it makes finding their original trajectory incredibly difficult to decipher because it went through a lot of changes due to the various magnetic fields in space and around the Earth. So there are a few clues regarding cosmic ray origins. Cosmic rays must originate from within our own galaxy because the numerous magnetic fields in our galaxy are strong enough to retain them within the confines, and only a few exceptions of the highest energy cosmic rays could have come from outside our galaxy. by looking at the rarer cosmic nuclei like lithium, beryllium, and boron, which were formed when carbon, nitrogen, and oxygen strike an interstellar proton. We can estimate that cosmic rays travel for nearly 3 to 10 million years on average, or roughly 30 times around our galaxy before they interact with the Earth's atmosphere. And due to their high speeds, it's well assumed that the best candidate for these cosmic rays are those super energetic explosions like supernova, and this leads to these charged particles then being accelerated into interstellar space at high velocities. So, in this lecture, we really emphasize that the interstellar material is not static. It's not doing nothing. It's going through a lot of processes and being affected by many other processes throughout our galaxy. And so it's changing its dynamics over time, going from hot to cold, fast to slow, dense to sparse, and so forth. But the interstellar material within our own galaxy is not a closed system. When this material collects into large nebulous clouds, these gases collapse and form stars, which lock the material within the star until eventually that star dies and re ejects that material out into space. On average, one third of the matter within stars will eventually go back into interstellar space, some of which can be ejected from the galaxy itself. This process is known as the cosmic baryon cycle. It is a process of accumulating more baryonic matter from intergalactic sources, using that matter to form stars and stellar systems within our galaxy, and then re-emitting a fraction of it back into intergalactic space. So this is, as a galaxy evolves, sometimes it collides with and absorbs smaller dwarf galaxies, or even collides with galaxies of similar sizes. So we know that our Milky Way galaxy is going to collide with Andromeda in several billion years, and so that's going to introduce a lot of new interstellar material as these two galaxies collide and mix and merge together. So that's really going to kickstart our cosmic baryon cycle in our own Milky Way galaxy again. It's really going to drive new star formation. Now let's talk about our own backyard, what we call our local bubble. So interstellar material is distributed throughout the universe in bubbles, these little gaseous regions that we've been talking about. And within our own stellar neighborhood, we have the local hot bubble, nearly 1 million degrees. This is an H2 region. But this local bubble has very little material, and so this high temperature is really not affecting its surroundings. This is really more of a statistical temperature than something that you really experience. Scientists conjecture that this formed near the Scorpius and Centaurus constellations, where many star formations took place, and the most massive of these stars would then explode in the interstellar medium. So this created an expanding super bubble which reached the sun 7.6 million years ago and now stretches 200 light years past the sun. So this bubble has drifted into our own local space, and our star has drifted into it as well. Other local clouds exist within our local bubble, and the sun itself is entered a cloud nearly 10,000 years ago, which is referred to as the local fluff, which has about an average temperature of 7,000 Kelvin and a density of about 0.3 atoms per cubic centimeter. While the local fluff is a very thin cloud, we estimate it contributes 50 to 100 times more particles than the solar wind to our solar system, which have been detected and counted by spacecraft as they travel between the planets. So as spacecraft travel in our own solar system, we are actually able to learn a little bit about our areas around our solar system, because our solar system is traveling through space, and so we can learn so much about our local environment just by studying it. It's really cool, and it really points to the power of these missions to tell us about our local universe. This brings us to the end of our lecture on the interstellar medium.